So this is the next episode, the third episode about the bin packing problem. In the first one, I showed you how to create a mathematical model. In the second one, I showed you this mathematical model. The second one, I showed you how to create an implementation in Python and Gurobi of this mathematical model. And we tried solving some of the instances. Right here is the Gurobi Python model. And we tried to solve some of the instances. And one thing I wanted to add here is also to have the solution exported. So we return here from the model objective value and the best bound, but it will also be interesting to return the solution. And the solution can, for example, be returned by assigning, by saying, what is the bin for each item? Let's call it bin for item. And this would be an array, a list that has the bin number for every item I, right? It will completely define. So if I know for item 0, the bin is 5, then I know this item is in bin 5, and so on for each item. So I'm going to first set it to -1, indicating I really don't know yet for I in range n. I will just fill it with values -1 for every item. And then what I will do is I will say, for I in range n and for j in range ub, if the value of variable xij, the value which we get through, remember, attribute x, if this value is 1, so I mean I expect it to be either 0 or 1, but remember for numerical purposes it's better not to compare with equality, but if it's more than 5, then it must be 1. If it's not more than 5, then it must be 0. So if it's more than 5, so if it's 1, then I know I can set bin for item I is j. And then I can also return it. So I return here objective value, objective bound, and bin for item, right? And then if we run this, and let's try and run this, let's say for something reasonable like 15 seconds. 15 seconds, maybe let's keep it 30, but I'll change the parameter here. Model run for 15 seconds, and perhaps without showing, log to console has to be changed. Log to console and time limit in seconds. So if I run this again, I get this solution, which, right, it's a little bit unclear because it's such a large array here, but it gives me the number of bins used 203, the lower bound 198, and this is the assignment, so that means that item 0 goes in bin 166, item 1 goes in bin 360, and so on, right? I don't think I will be printing it. All I will be doing is I will just say n bins and n bins lower bound equals, and then bin for item. I'm going to do this and then print number of bins equals n bins and number of bins lower bound equals not b bins, n bins lower bound, right? So I just want to running it again. And after 15 seconds, this is what I'm getting. Number of bins is 203, number of the lower bound is 193, but we also have the solution, and if we wanted to, like, say, display it or check if it is actually correct, then we would actually know, we could display it, for example. Now, in this video, I want to show you how to create a heuristic. Basically, you know, this is solving this problem. One way to solve this problem is to formulate this mathematical model, right? Implement it in a solver, and get a solution of it. But as you can see, it is not working very well for us. It's not finding an optimal solution. And also, even to find a reasonable solution takes quite a few seconds. If this problem was, if the instance was even larger, let's say if we try the last one, which has 1,000 items, it would actually take a long time just to give us the first solution, because the problem would be the mathematical model would have so many decision variables and constraints that it would take a lot of time to just solve this, get any solution out of it. So how can we define a heuristic? Well, I'm going to create another cell here, code cell, and then I'm going to define a heuristic as follows. It will be a function. So first of all, I will start from similar things. I'm going to get the number of, right? I'm going to assume there is W and C. So as before, I'm going to assume that that there is W and C defined. So let's say, let me actually change it here. I will say C and W are extracted from the data, and then I are passed here to the model a simple C, W, and the other parameters. Right? So again, as before, I'm going to assume I take one of the data sets. I take the C and W from this data set. I calculate N, and then I'm going to run the heuristic. And the heuristic is going to be as follows. I'm going to first sort the items by decreasing weights. Why would I sort them in such a way? Well, it makes sense to start packing from the larger items first, because if you pack small items first and you fill up some of the bins, then it's going to be difficult to add any large item because the residual space will be small. If you start from the largest and leave the smallest to the end, it is easier with the smaller items to later squeeze them into residual spaces, right? So what I will start with is first sorting the items. So how can I sort the items? Well, we can say there is an order of items that is a sorted array, right? And what are the items that I can define an empty array of items, not empty items, just item indices I for I in range n, right? This is just an array that will be 0 to n minus 1. And I need to sort it, but what do I sort it by? Well, I have to give it a key, and the key can be given by the so-called lambda function that takes the index I and returns weight of I, right? So if you do this, this is going to actually sort these indices I's in an order of increasing weights, but we in fact want them to be decreasing. Right? So if we want decreasing, we need to add one more parameter to the sorting function, the sorted function. It's called reverse equals true, right? And so reverse equals true is the parameter that will actually sort in the reverse order. So instead of increasing weights, it will be sorting them by decreasing weights, right? So if I actually run this and display the order, let's see. Well, in fact, the order is 0, 1 up to something very large number. And the reason for that is that these items are actually already sorted, decreasing. You can see here 98, 93, 92, 90, 86, 85, and so on. So they are already sorted by decreasing or by decreasing or actually non-increasing, 98, 98, 98, and then 96, and so on. Right? So the order, this sorting actually doesn't do much, but if you had other data and perhaps the item were not sorted, then this order is important. And then what we need to do is as follows. We need to go for each I in order, and we need to try to pack it in one of the bins. But what are the bins and what do they contain? So first of all, we need information here, something like bin for item, right? As before, I can say -1 for I in range n. Initially, items are not packed. So the bin for item is -1, indicating I haven't yet decided the bin for item I. And also what I want to do is I want to save how much space there is in a bin still, right? So I'll have an array bin space, And what this array means is it contains, first of all, for every bin that is currently created, it has one number, how much space there is still in that bin, right? Now, initially, I have no bins, so this array is empty, but later on, I will add here something like a value C to open the first bin, and then when I pack an item, so let's say it's 150, when I pack an item that has size 98, this will be decreased to 52, and so on. And then when this bin is full or almost full, let's say it has only 3 units of space, nothing, then another 150 will be added, and so on. So initially this is empty, and then I will do what as follows. If I take an item I will try to pack it in every bin j, for j in range, as many as I have open. So length of bin space, this is how many bins I have. Remember, initially it's 0, but later on this bin space will be filled. There will be some, let's say 5, 10, 20 bins that are open, right? So j will go over all those indices of bins. And then what I will try to see is if the weight of I, of this item I, if it actually fits, so it's less than or equal bin space j, right? So if I go over those bins and I see, oh, item I still fits in bin j because its weight is smaller or equal to the bin space, then I can pack it in this bin, right? So I can say bin for item I equals j, right? But also if I pack it, I need to adjust the space. So I need to say bin space j minus equals wi. So what that means is the bin space is now reduced because the item is packed. So next time we get to this line, there will be less space, and maybe another item will not fit there, right? And we'll have to move to another bin. Now, because I've already packed this item I no longer want to check the next j. To stop this for loop, to stop it, you can put a command break. And this break will mean, oh, now you packed the item, stop this for loop, but not this one. This one will be continued, so we'll move to the next item. So at this point, what might be the result? Either we go through all the bins and we find one of them where the item fits, and then we pack it there, or we go through all the bins and it doesn't fit in any of the bins, right? And so what that means is we need a new bin. So how can we check if it was packed in anything? Well, if bin for item I is negative, right? Meaning the -1, as we saw it here, -1 initially, right? So no bin could accommodate the item in this loop. Then we know we need a new bin. So we need to say j equals length of bin space. This is actually the number. Notice if bin space, let's say, if there is 5, I don't know, some 5 numbers, right? And so that means there are 5 open bins, but those bins, the indices are 0, 1, 2, 3, and 4. So if I take j equals length of bin space, that will give me 5, right? So that gives me index 5, and that's an index of the new bin. And then I can say, okay, so now item I goes into this bin. So bin for item I is this new bin j. And then bin space in this, right? The bin space still doesn't have this space for the last bin. We should add here the value c minus weight of item I. So we will say bin space append c minus wi, right? So we add, there is space c, but we immediately decrease it by wi because we already added this item I here to this bin, right? So of course these comments are just for a particular case. I have to still go back to this being an empty thing. And then, so how does this work now? The way this works is we go through all the items. And initially, of course, bins, there's no bins open. So the first time we get here, this is not going to work. There is no bins to pack this item. So the first item will definitely result in opening a new bin in those lines. So there will be j equal bin 0 will be created, and then it will be packed. The item will be packed in it, and then the second item will be considered. If it fits with the first item in the same bin, it will be added here. If not, another bin will be open, and the loop will continue like this. These structures that I created, bin for item and bin space, these are just my structures, the ones that I thought of defining. And actually we can see at the end, for example, what's bin space. Let's actually try to do this for instance 0. So for example, you see at the end, bin space contains these numbers, which means there are 2 units unused in the first bin. Second bin is completely full, then 1 unit unused, and so on. In the last bin, we still have 96 units of space, right? And actually, we can see length of bin space is 23. So actually, we found a solution of 23 bins for this instance number 0. If you recall, I think we had solution 22 using the solver, so this is actually worse. And let's see also what is the bin for item array. And you see it is 0, 1, and so on. And then again, there is, for example, 8 here. So there is, these items are packed in consecutive bins, and then sometimes we pack, for example, here we get to an item where 2 items go into bin 13, and then another one goes into bin 10, and so on. Right? So after this, right, we could return bin for item, and that tells us, right, and we could also return, for example, a number of bins. Number of bins will be length of bin space. Let's actually, so let's assign this n bins. Number of bins used is going to be length of bin space, and then n bins. We will return it, and bin for items. Obviously, this now has to become a function, so I need to make this function. Now I'm going to call this heuristic, and I'll call it FFD, first fit decreasing heuristic, CW, right? And so this is first fit decreasing heuristic. This is a well-known heuristic for bin packing. And why is it called first fit decreasing? Well, decreasing is because we sorted items in the order of decreasing weights. So for this line, right, this is sort by decreasing weights. And then we pack them in the first bin in which they fit. So pack in the first bin in which the item fits. And then if no bin can accommodate the item, open a new bin, right? So that's how this works. This heuristic works. And so again, we can see now, like we did here before, let's take this. Right, as we solved before the instances, we can now solve them with this heuristic. So we can say, let's extract one of the instances, and let's run heuristic FFD CW, and let's get the results, number of bins, and bin for item, and let's print the number of bins. Print number of bins, right? So we get number of bins, heuristic found a solution with n bins, right? And then we can run the exact algorithm the same way. So we can take the model, and we can say the same CW, maximum limit, let's say 5 seconds, and we can say model found a solution with n bins, right? So you can see heuristic found this, but the model found this, right? 22 rather than 23, and the lower bound is 22. So the interesting case is, of course, if you try this instance, let's say number 5 that we did try before, and if you run it just for 5 seconds, you see heuristic found with 201 bins, whereas the model finds 346. If I try 15 seconds, then after 15 seconds, let me pause. After 15 seconds, you see the exact model still found only 203, a solution with 203 bins, whereas the heuristic found 201, right? So sometimes the heuristic can actually be better than the exact model because it is written specifically for this problem. And so this is the advantage of the heuristic. But the other advantage is that notice what happened before. The upper bound that we used was 500, because we said a trivial solution for the bin packing is packing each item, each of the n items, 500 items, each in a separate bin. So the upper bound, the number of bins at most will be 500. But now, if we have a heuristic, we have additional information. We know that we can actually use just 201 bins, or maybe less, right? We don't know. The heuristic doesn't guarantee optimality. It doesn't have to be the best, but it is something that tells us the upper bound is 201 because we already have a solution of 201. So the interesting thing here is that we can now modify this model, right? So we can say, let's provide to the model the initial solution, what we got from here, right? So we could actually say, instead of using upper bound, just use the n bins from the heuristic, right? So I'm going to go to the model and redefine it and say now the upper bound comes from outside. It's not calculated inside, right? And then we can actually solve it for the new upper bound. And let's see what effect will that have. And so let's compile this and then run this again. And if we run this again, and let's say for 15 seconds, I'm going to show the log now. Okay, so again, this is running. And notice with an upper bound now is 201. And actually, the solver very quickly found a heuristic solution with 201. And it is now running and trying to prove or improve the solution of 201. Well, 15 seconds was not enough for it to improve it. But perhaps if we run it a little bit longer, let me try, let's say 60 seconds and try to run it. And I'm going to pause. So after 60 seconds, you see that the solution is still 201. The solver did some exploring of the branch and bound tree. It tried to search for better solutions, but it couldn't find any better solutions. But the good thing is that the model now is smaller because we are assuming the number, the indexing for J goes up to 201 only. And so the model starts solving faster. And as you can see, it is still very difficult to prove to optimality. After 60 seconds, the solution is still not proven optimal. There is still a gap, right? The best solution we have is 201, but we still don't know if it is going to be better than, it could be improved by at most 3 bins, right? It could become 198, perhaps, we don't know. We would have to solve this to the end and not limit the time to 60 seconds. There's one more thing that one can do with this solution, and right, you see that actually the solver is smart enough to find a heuristic solution from the on its own that fits with 201 bins. But in fact, we could give the solver here as a parameter to the function. I can give the solution bin for item to the model, and right, and let's call this let's put here after the upper bound, I can also give bin for item. And bin for item, this is the initial solution. So what that means is that I have an initial solution that I can give to the solver. And this means that I can initiate values of x and y to some initial values and basically help the solver. Instead of asking it to figure out on its own what the optimal solution, what the initial solution, heuristic solution is, I can give it the solution. And to do this, you can use an attribute of the variable called start. And so what we can do this as follows. We can say for I in bin for item, for range n, for each item, we know item I is assigned to bin for item I. This is the I, right? This is the bin for to each the item is assigned. So I can say that xi for this j, right, xij dot, and the attribute is starting value equals 1, right? So by doing this, actually I can even shorten it. I can say replace this here, right? What we're saying here, set this value, this decision variable to 1. Notice we're not setting some of the decision variables to 0, the values for other x variables, right? This is for a particular j, but not for all j values for this particular item. However, the solver, with this hint and knowing the constraints, it can figure out that the other decision variables that we don't set, they all have to be equal to 0 because there is a constraint. For every item, there can only be, the sum is equal to 1, so there can only be one bin to which it is assigned. And therefore, it actually can figure out what the values of the other x variables are and what the values of y variables are, and therefore it can actually guess the full solution from it. So let's try to compile this, and let's run this again and look at the code here. The solver said found heuristic solution with objective 201, but if we run it again, it will say mip start produced solution with objective 201. So it loaded this solution, and then it continued to just knowing it rather than guessing it from some internal solution. So it is again running, and still, unfortunately, after 60 seconds, it is unable to improve the solution 201. But as you see, we can use a heuristic here for the mixed integer model to provide an upper bound to reduce the number of variables, right? And the other thing is we can actually provide a starting solution to help the solver get a good solution to start with.